Relativistic Doppler effect is a relative measure of recessional speed v compared to speed of light c of a celestial object that is carried by the Hubble flow and is found from equation z, which is equal to the square root of 1 plus v over c divided by the square root of 1 minus v over c, and all of that minus 1. Where z is equal to delta lambda over lambda lab, delta lambda is equal to lambda observed minus lambda lab. Lambda observed is observed spectral line wavelength from a distant celestial object being carried by the Hubble flow, and lambda lab is the same spectral line, but at a wavelength found in the laboratory. So let's take a look at this relativistic Doppler effect. It is a relative measure of recessional speed v. So our goal here is to find speed v. And we're going to find it using this equation here, which is based on z. Z is equal to the square root of 1 plus v over c divided by the square root of 1 minus v over c, and all of that minus 1. So once you know speed c and z, all you need to do is solve for v. C is a speed of light, you already know it, so you need to solve for z. Z is found from this equation over here, which is equal to delta lambda over lambda lab. Delta lambda is lambda observed minus lambda lab, and lambda observed is an observed spectral line wavelength from a distant celestial object being carried by the Hubble flow, and lambda lab is the same spectral line, but at a wavelength found in the laboratory. So let's take a look at some spectral lines. Here we're looking at spectral lines observed in the sun, which we're going to take as lambda lab. So each line that you see here is a wavelength that is measured in the lab, and it's based on the sun's spectrum. We get a spectrum of a distant object that is being carried away by the Hubble flow. So this object is very far away, and it has a high recessional speed v that we want to find. So we get the spectra from this object, and then we notice the shift in the lines. Same lines appear in the distant object and in the sun object, but we want to find the shift in the lines. Notice that all the lines from the far away objects are shifted to the right, or the red side of the spectrum, hence redshift. And the more shift there is, the faster the object goes due to the Hubble flow, and hence we have this relativistic part of the Doppler effect. So what we need to do is we need to measure the lambda observed. So let's say we're taking a look at this red line. So we're just going to extend this red line up and into the lab line. And our goal here is to measure the shift in the two lines. We've got lambda lab from the sun spectrum on the left, and we have lambda observed from the observed spectrum below that had just moved up here, so we could figure out the shift in the line. Once you know delta lambda, you plug that into this equation to solve for z. Then you plug z into this equation to solve for v. And we get what's known as the relativistic Doppler effect, solving for the recessional speed v.